here, let me read out for you. A rectangular copper sample is subjected to 30 Newton stress, and the voltage value read off from the device is 0.060 millivolt per volt, and strain gauge sensitivity is K 2.05. Please calculate strain and stress values. Okay. Now let's remember the mechanical properties of metals. Here, stress is expressed megapascal, and this one is strain. Dimensionless is expressed millivolt per millivolt. Okay, or it could be expressed in percentages. Here. And up to this point, what is the name of this point?
Yield point.
Yield point. That's lovely. Yield point. And up to yield point, okay, there is elastic strain. Two atoms you stretch, becomes like that. You never break this bonding, okay? You only stretch. When you unload, okay, it goes back to its original position. Am I right? It goes back to original position, and that's why we call it elastic strain. On the other hand, in the plastic region, this here, when you apply load, when you increase, when you exceed this point, then you become, you proceed to plastic region. When you apply load, you stretch after certain degree, okay, this bonding is broken. This bonding is upset, okay, this upset, and then new bonds are formed, okay, and this is the reason why we call it plastic region, and there is no going back, okay, new neighbors are obtained. Here, and this is the tensile, the maximum stress that the material can endure, that the material can tolerate. Okay, when you unload, the material goes back to here from this point, goes back to its original position. Here, this is plastic region, and what is the name of this point? Fracture, right? Fracture takes place here. This is maximum tensile stress, and this is the fracture stress. And what is the name of this area? Arkadaşlar konuşabilirsiniz.
Elastic region.
No. This specific
Toughness.
Actually, toughness is here.
Resilience değil mi?
That's right. This is toughness. Okay, this is toughness, and this guy is resilience. And this is toughness. Resilience is the mechanical properties that the material can endure without without being subjected to plastic deformation. Okay, up to this now, this is plastic deformation takes place, and here fracture takes place. This is toughness, and this one is resilience. Okay, what happens up to this? This is stress, and stress is equal to, what is it?
Elastic modulus.
Modulus of elasticity, right? Like, you know, in the physics course, you remember K value in the springs. Actually, the same thing, okay? The more stress you apply, this is constant, okay? The more stress you apply, the more strain you will get, okay? When you increase stress, then you get more strain. So it means that the material becomes longer. It elongates. Okay? Now, why I'm talking about these kind of things? Because there is a relationship between mechanical properties and electrical properties. So when you elongate the material, what happens to resistance of the material? Direnç ne olur arkadaşlar?
Artması lazım.
Direnç artar. Değil mi? The resistance increases due to plastic deformation. So let me show you something here. I'd like to show you there is some devices. This is called strain gauge. Can you see it? And using this strain gauge here, strain gauge, there is a tiny small resistance over there. And when you change here, strain gauges, when you change the resistance, you get a potential difference. From this potential difference, you can get the strain value. From the strain value, if you know the stress, then you can calculate modulus of elasticity of the materials. Okay? Okay, let's go back to our page. This is R times L A. This is length of the material. Okay, let's say copper wire. And this is the cross-sectional area. This is specific resistance, and this is the resistance of the material. Am I right? Formül doğru mu arkadaşlar?
Yes.
When we derive this equation, okay, dr is equal to d rho times L and dl times okay, this is the derivation of this equation, and we divide this equation to R is equal to rho times L divided by cross-sectional area, and then we will get this cancels each other. This would be A and A. Can you follow?
Yes.
Okay, and dA, this is cross-section area. A is equal to P squared times diameter, square diameter for dA is equal to dd. So instead of this, I could write down here. And dr divided r is equal to d rho dl and minus 2 just a second dt. And we could, instead of dr, this means delta r is equal to r rho udl actually delta d is equal to minus Poisson ratio times delta L divided L. You know Poisson ratio, right? When you apply stress in Z direction, okay, epsilon Z is equal to delta L divided L0, okay, and epsilon X, delta X divided X0. And there is a relationship between this one and this one, and we call it Poisson ratio. This is minus because it never gets longer, okay? It shrinks. This is the reason why we write down here minus epsilon x, epsilon z, also epsilon y, epsilon z. Okay, and Poisson ratio. Instead of this one, I could write down here minus Poisson ratio times delta L and L. And then dr, this is difference in resistance divided by initial resistance of the material is equal to 1 plus 2 Poisson ratio plus delta G, and this is difference in specific resistance divided by the specific resistance times L delta L times delta L L. And we call it here K, and this is called strain gauge sensitivity. In our question, we will take K is equal to 2.05. So we will get here delta R divided R is equal to sensitivity times delta L, and we know this is our strain value, and this is the difference in resistance due to what? Due to elastic deformation. When you deform the material, resistance increases and strain increases. So here are relationship. This is mechanical behavior and this is electrical behavior. So there is a link, there is a relationship between mechanical properties of the material and electrical properties of the material. Okay, any question? Now let's go back to question. A rectangular copper sample is subject to 30 Newton stress. Our stress level is, the force is, load is 30 Newton. And the voltage value is read off from device 0.016 times 10 to 3 volts per volt, and strain gauge sensitivity K is 2.05, and then we can calculate strain value, also stress value. Here, instead of resistance, here we can use this device voltage value. Why we get the voltage? Due to the difference in resistance. Okay, when you change the resistance, then you will change the voltage. If you read off the voltage difference, here is the difference, voltage difference, then you can use this formula and we can calculate the strain value. And here, one plus 0.33, this is the Poisson ratio, times 4 divided by 2.05 and 0.016 times 10 to minus 3. And this E value (1.17 times 10 to minus 5 millimeter per millimeter). What I'm saying here is, this is an important point I'd like to mention, that you cannot measure this small amount of strain, okay? But you can measure R value or voltage difference. So indirectly, ladies and gentlemen, indirectly you could calculate strain value, which is 1.15 times 10 to minus 5 millimeter per millimeter. And from this also stress value could be calculated. F divided by cross-sectional area, and rectangular sample 2 millimeter times 10 millimeters, and this would be 1.5 Newton per square millimeter, so 1.5 megapascal. Pascal. And furthermore, we could also calculate modulus of elasticity. Okay, we calculated from the question. This is 1.5 megapascal, and modulus of elasticity time strain value 1.17 times minus 50. So is about gigapascal. Actually, is about 1.20 gigapascal, 120,000 megapascal, and the modulus of elasticity could be calculated quite easily, indirectly. Okay, and this is the reason why we could calculate the resistance, and indirectly we could calculate the strain value, and from strain value and the stress that we know the applied stress, and we can calculate the modulus of elasticity. If we know the modulus of elasticity, for copper, is about 120 gigapascal, and when we know the strain from this formula, then we can calculate this one, and finally we can calculate stress level of the sample. Any question?